I'm glad to be here today to talk about our funded project, weekly supervised federated graph learning for cyber-physical systems. So this is outline for my today's talk. So first, I will give a brief introduction about what is federated learning, right, and also what is weekly supervised federated learning, and why, and also discuss why we need to develop some new techniques along this direction. And then I will also I will mainly focus on discussing two pieces of our recent works. So as a result of this project, so both works are published in the CKDD conference. It is a premier data science conference, one in last year and the other one in this year. So for the first piece of work that I will present a new weekly supervised federated learning framework that enables fusion learning, right? So the models can generalize to clients with limited training samples. And secondly, that I will also discuss how can we enable the federated learning on the graph or the relational data. So in particular, that I will discuss how to explore some strategies for training the federated graph machine learning models, right? So especially targeting on the nodes from the minority classes, so where the training samples are also limited, right? So basically, you can see that we will discuss two different kinds of situations regarding the weekly supervision. Okay, and at the last, I will give a conclusion, and if time allows, I will also discuss some future research directions. Okay, so let's get started. So what is federated learning? Right, so generally speaking, that federated learning is a very powerful learning framework, right? So that it can be used to enable the distributed model training. So in federated learning, typically we have different data owners. So these data owners are also called the clients in certain situations, right? So for example, that these data owners or the clients could be the mobile devices, can be the sensors, can be the edge servers in a cyber physical systems. And these clients, they want to collaborate together with each other to train a shared machine learning model while keeping their private data to be localized. Okay, so typically that this kind of training process is orchestrated by a central server, right? So because that we don't want to share the data between the clients and the central server, so only the model parameters or the gradients will be transmitted between the data owners and the central server. Okay, so this is a quite typical example about federated learning, right? So imagine that you are using some keyboard app on your smartphone. So these apps will provide the next word prediction, right, for you, right, to help you to type faster by suggesting the next word based on what you have already typed so far, right? So these predictions typically are powered by some AI or machine learning models that have been trained on vast amounts of text data. However, that sending some raw typing data from the user to the central server may raise some significant privacy concerns. Right? The users may not feel comfortable to share their personal typing data, which could contain some sensitive information. So in this case, that federated learning would be an ideal learning paradigm to tackle this kind of problem. Right? So in federated learning, that one typical type of federated learning is called the cross-device federated learning. So here that the participating clients are typically some small devices, like the mobile devices, IoT devices, right? They are quite common in the cyber physical systems. So there are some characteristics for the cross-device federated learning. So for example, in this kind of situation, typically we often have a large number of clients, right? And the device or the clients may not always be online or available, right? So they might join or leave the training process at any time, right? And additionally, that because that there are some small devices, So the connections between the clients and the central server may not be quite reliable. And each client may also have limited computational resources to support the training task, right? So there are many successful examples of the cross-device federated learning, right? So in addition to the next word prediction problem I just mentioned in the smartphone, another example is about the personalized digital assistants, right, such as the Amazon Alexa voice, right? So for example, to enhance the personalization, so Alexa needs to learn from the user interactions, right? However, that sending some detailed voicing data or the interaction logs to a central server may raise some privacy concerns, right? So users may not want their voice commands or the personal preferences shared with or stored by a central authority, right? So in this case, that we can leverage the cross-device federated learning. So in addition to the cross-device federated learning, another type of federated learning paradigm is called the cross-silo federated learning. So in cross-silo federated learning, that the clients are not small devices. So typically that there are some example, there could be some hospitals, the banks, universities, governments, right? So for this kind of situation, that we often have a relatively small number of clients, and the connections between the clients and the central server are typically more stable, and we usually have more data for each institution or each organization. Okay, and there are also many successful applications for the cross-silo federated learning. Right, so one application is about the clinical diagnosis in medical institutions. Right, for example, we can see that different hospitals or medical institutions, right? So they have their private data for their patients. They don't want to share the data with each other, but they still want to collaborate together to train a machine learning model for diagnosing the disease, right, such as cancer or the heart conditions, right? So in this case, we can basically leverage the cross-silo federated learning. Another example is about the different banks, right? They may want to collaborate together to build a machine learning model that can predict the customer credit risk, right? Helping to assess the likelihood a customer will default on a loan or credit card payment, but their customer data is quite sensitive. They don't want to share this kind of data, right? Okay, so this is a very quick introduction about the federated learning. So next, I want to provide some motivations for our proposed works that focus on weakly supervised federated learning. So we can see that although federated learning has achieved quite remarkable performance in many situations, so here that we argue that most of the existing methods, they generally assume that we have sufficient data, right, to enable the collaborative training for each client. However, that in many practical situations that we may have limited data samples for the training, right? So this kind of the problem is also called the weak supervision problem in traditional machine learning. So let's consider the following example, right? So this is basically federated learning systems in the healthcare. Suppose that we have many chest X-ray image samples, right? So they are labeled as some common disease categories like the lung-cancer, pneumonia, right? So different hospitals that they have the medical images from different patients, right? They want to jointly train a chest X-ray image classification model, right, to classify the medical images, right? So in this case, we can see that some commonly encountered class labels like lung cancers, pneumonia, because we have a large number of data for these classes. So they are called the base classes, right? And let's assume that one day a new disease is discovered. Let's say it's COVID-19, right? So at the very beginning, that we don't have a sufficient sufficient amount of training samples for this new disease, right? But still that we wanted the model to, let's say, can generalize to this new disease, right? To detect whether the patient has this COVID-19 disease or not, right? But because that we have limited training data for the COVID-19, typically that the trained machine learning model, especially the federated learning model, cannot provide good generalization capability, right? So in this case, that this new disease, like the COVID-19, they are called the novel classes, right? For the novel classes, we have limited label data. Okay, so as a summary, that here are some basic properties for the base classes and the novel classes. Right? We can see that for the base classes, they are quite common during the training. Right? We have abundant label samples, right? So and also for the novel classes, they are unseen during the training. We have limited label data, right? So this kind of the novel classes could also be quite different across different clients. Okay. So this is another example about the Google photo categorization. Right? So here in this example, that the central server aims to learn an image classification model from the photos distributed across a large number of clients, like the mobile devices. Right? So in this situation, we can see that some common image classes like the cats, dogs, chairs, right, furnitures, they could be considered as base classes. While for some new image classes, like new electronic products, right, so they are often considered as novel classes. We have a very limited amount of data for them, right, but still we want to achieve good classification performance for these novel classes. So then the first challenge for this work we're trying to address is that how can we classify these unlabeled samples in novel classes with limited label data? Okay. So the second challenge of the weakly supervised federated learning is about the structural heterogeneity when we consider the graphs or the relations between different entities. Okay, so so in this example, this is basically about federated learning systems for across different banks. Right. So here we can see that each bank in the systems has its local customer data. Right and the transactions between the customers, right? So which can naturally form a graph, right? So for example, this bank is close to the hospital systems. We can see most of its customers are the doctors or the nurses, right? So here that our goal is that we're trying to train a powerful graph-based machine learning model, right? That can be used to predict the credit risk for each customer, right? So in this case, that we can leverage some existing very popular graph-based machine learning models, such as graph neural networks, right, to basically trying to learn an embedding or vector representation for each node in the graph, right? Based on the node representations, then we can basically make the predictions, right? So, but the problem here is that let's say for the graph neural networks, right, the basic working mechanism is called the information aggregation mechanisms. Right? If you want to learn an embedding for each node, so typically we're trying to aggregate the information from its neighbors, right? And then we do multiple layers of the message passing, then we can get a more informative representation for each node, right? But the problem here is that for this kind of the relational data, the information aggregation mechanisms may have different impacts on the nodes from the majority classes and the nodes from the minority classes, right? So here we can see that for the bank A, right, as I mentioned, most of its customers are the doctors, right? But here we have another customer, which is a teacher. Right? We can see that for this teacher, most of its neighbors actually have a different class label than her. Right? So basically, when we do the message passing, so basically that for this particular teacher, it may receive a lot of adverse neighboring information. So eventually, it will need to some underrepresented node embeddings for this particular teacher in this graph, right? So then, if we do the classification, basically we may not have very good performance for these minority nodes. Okay, so to dig deeper into this issue, we can also compute the so-called node homopholy value. So here we define the node homopholy value as the ratio of the surrounding neighbors, right? So for each node, we want to look at the ratio of the surrounding neighbors that have the same class label as this particular node, right? So then we can also observe that on average, typically for the nodes from the majority classes, so the node homopholy value actually is much higher than the nodes from the minority classes. Okay, so here is some detailed evidence. So in this example, we synthesize a federated learning systems by splitting a graph data into different communities via a community detection method. So here that we consider each community as a client, right? So for the left table, it shows the distribution of the majority classes and the number of majority nodes and the minority nodes and their corresponding average homomorphic values. Right? So here we can see that across 7 different clients, right? So for the nodes from the minority classes, their average homomorphic value actually are significantly lower than the nodes from the majority classes, right? So it means that for these minority nodes, that they will basically receive some unfavorable neighbor information, right, during the message passing mechanism of the GN models, and they have a high chance to be misclassified. So to further validate our conjecture, we also perform some collaborative training for the MLP model and the GNN model, following the standard federated learning method, like the federated averaging. So here on the right figure, we can see that on average, but across all the nodes, for the GM model, actually it has a higher performance than the MLP model, because this is very easy to understand because we leverage some additional relational information among different nodes. But then for these different bars here, we can see that we focus on the minority nodes, right? So we only look at the minority nodes across 7 different clients. So we can see that on these minority nodes, right? So if we make use of the GM model, actually its performance actually is quite lower, right? Even lower than the MLP model, right? So actually we kind of get a kind of the contradiction here, right? So this kind of contradiction is mainly because that for the minority nodes that they actually their neighbors are from a different class. Okay. So then the second challenge we're trying to address this talk is that we're trying to mitigate the impact of the adverse labeling information for the minority nodes. And we're trying to ensure that for the minority nodes, we can also get good classification performance. Okay. So next, I will start to discuss the first piece of work about the federated learning with the future data. So traditionally, that the meta-learning is a popular way to deal with learning tasks with limited training samples, right? So, so here that in meta-learning, so the basic idea is that we focus on the few short classification problems, right? So this is basically an example. We call it a meta test task. So basically, we have limited label data for each class, right? And here that each meta task also contains a small number of label data as references and unlabeled data for the classification. So they are also referred as the support set and the query set. And so for example, for the support set, if we have 2 image samples for each class, so it's called the two-way too-short problem. Okay. So the basic idea for the meta learning is that we want to learn some meta knowledge from some base classes. And for the base classes, as we mentioned, they have abundant label data, right? And then we want to ensure that this kind of the meta knowledge learned across the base classes can be generalized to novel classes with limited training samples, right? So this is the basic idea. So, but the problem here is that directly apply the meta learning to the federated learning situation may not be quite practical. So there are 2 major challenges here. So the first challenge here is that because for each client, we have a very limited amount of data, as we mentioned, right? So due to the local data insufficiency issue, right, it is quite non-trivial to learn some meta knowledge from each client, right? So we call it the local data insufficiency issue here. And the second issue here is that because the data distributions across different clients could be quite different, right? So therefore that when we do the aggregation of the local models on the central server side, right? So typically for the federated learning, we need to aggregate the local model at the central server. So this kind of aggregation will disrupt the learning of the meta knowledge, right, for each client. So in the other words, that it is hard, very difficult to learn some unique meta knowledge for each client, right? So we call this kind of problem to be the global data variance issue. Okay. So to address this kind of problem that we propose a decoupled meta learning framework. So this work is led by my PhD student, Song Wang. So the basic idea for this work is that it will include two type of models. So we have a client model, and we also have we have a server model. So the basic idea is that our proposed framework will retain a unique client model for each client, right? So we can see that the client model basically will retain in each client. It will not be shared. So this client model will be used to learn some meta knowledge. Then there is also a server model. My server model basically will be shared and transmitted between the client and the server, right? So this shared server model will be used to learn some client invariant knowledge. Okay. So the client model is, as we mentioned, so client model will kept locally. It is used to classify the unsupported classes in each meta training task, while the server model, basically, it will be used to classify all the classes that it has encountered so far. Okay, so this is a basic workflow for our approach, right? So we can see that there is two different workflows. There is a client model flow and there is a server model flow. Right, so client model flow, basically, it will each client will receive the server model from the server at the beginning of each round, and then the server model and the client model, both of them will process the support and the query samples. And then we also develop some specific strategies to update the server model and the client model, right? And after this round, that the server model will be sent to the server for the model aggregation, while the client model basically will be kept locally, right? So this is a basic idea. So more specifically, as we mentioned, that we propose some specific strategies to update the server model and the client model, right? So specifically that we can leverage the prevalent meta learning strategies such as the model agnostic meta learning to update the client model in one fine-tuning step and one meta update step. And during the local meta training, we can also transfer the meta knowledge from the local client to the central server. So the meta knowledge can be leveraged by other clients to handle the local data insufficiency issue. And specifically that we can try to maximize the mutual information between the representations learned from the central server and the client model. Okay? And meanwhile, that to update the client model, we also develop another strategy we call the knowledge distillation, right, which are trying to guide the training of the client models. Okay, so here are some details for these two different updated strategies. I will just skip them. Okay, so let's look at some experiments. Right? So in the experiments, we actually perform the evaluation on both the text data and the image data, right? So we have different baseline models, right, including local model that basically perform the individualized training for each client. And we also adapt to meta learning models in a federated learning situation. And we also have another baseline models that combines the meta learning and adversarial training. Okay, so in this table, right, we actually we trying to show the classification performance for the different models, right? Basically, we can see that we have both the IID data split situation and the non-IID data split situation. So typically for the non-IID data split, the problem is more challenging. Okay. And also we look at different settings, right, including the one-shot learning, five-shot learning, right? So we can see that our method, we call the F square L, so it outperforms most of the baseline methods on different data sets under different situations, right, including the IID setting and non-IID setting and the different few-shot settings. And we can also see for the FL memo and FL prototype, So basically that for these two methods, we just adapted the meta-learning methods to the federated learning situation. So we can see that their performance actually is very similar to the local baseline, right? So this result also demonstrates that directly applying the meta-learning to the federated learning situation may not be quite effective, right? Because these methods are not essentially designed for the federated learning situation. And we also have some ablation studies, right? So here that we have different variants for our model, right? Including the variant that remove the decoupled framework, right? So basically that the client model will also be sent to the central server for the model aggregation. And we also have another two variants, basically remove the different updating strategies. So we can see from this figure basically that our model that includes all these design components basically achieves the best results. Okay. Okay, so this is the first piece of work I want to introduce, and also that I want to talk about the second piece of work, basically about the federated learning on graphs, right? So this work is led by my PhD student, Xinbo Fu. So as we can recall that we mentioned previously that for the graph situation, right? Basically, that the problem is that for the minority nodes that they have a high chance to receive some adverse labeling information, it will lead to some underrepresented embeddings for each node on the graph, right? And then the question here is that how can we obtain the desired neighbor information, right, especially for these minority nodes? So the basic idea here is that even though for some clients, let's say for the client A, which is close to the hospital systems, so this particular user is considered to be a minority, right? But if we look at some other clients, for example, for the client C, client D, right? So these two banks probably are more close to an education institution, right? So we can see that most of its customers are teachers or education workers, right? So in this way that although we don't have sufficient information regarding the teacher in the client A, but we can actually leverage the information, right, for the same class in the other clients, like the client C and the client D, right? So this is the basic idea. Okay. So this is our proposed federated learning framework. So we can see that given a graph GK that in the client K, so we can obtain each node's prediction, right? Through we can get each node's prediction through a GN graph neural network module, right? And then we can train the graph neural network module based on some ground truth information, right? And then we try to mitigate the impact of the adverse label information for the minority nodes. So what we can do here is that we try to learn an unbiased class-wise structural proxy. So in the other words, that for each class, we have a structural proxy vector. We try to learn a vector, right? So here that we consider that this kind of the structural proxy vectors can provide some high-level abstractions of labeling information for the nodes, right, across different classes. Okay. So then the basic idea is that we're trying to learn this class-wise learnable vector, these structural proxies. Okay. So then the question here is that how can we learn these structural proxies, right? So here we can see that we can feed the structural proxy and the feature information for each node into a feature structure encoder G omega, right? And then we learn another vector PK, okay? So we consider that the PK is basically a useful target, right? So that can be used to guide the training of the GNN model, right? So here we can see that we have a knowledge distillation loss trying to make use of the PIK to guide the training of the GNN model, right? And also that we also hope that this kind of the prediction target PIK is reliable, right? So to ensure that it is reliable, we can also try to distill some knowledge from the GM predictions, right? And here it comes with another problem, right? Because for the graph, right? So many nodes do not come with labels. Right? If we don't know their class labels, there's no way that we can get the structural proxy vectors, right? So then what we want to do here is that for these unlabeled nodes, we just make use of the node feature vector, fit it into a projector, to get another prediction target QRK. Okay, and then we can get the structure proxies for these unlabeled nodes by computing the dot product between this prediction target QRK and the structure proxies for the label node, right? And after we get that, we can also make use of the cross entropy loss, trying to minimize the difference between the between the ground truth and this prediction target for these unlabeled nodes. Okay, so by putting them together, we have another loss function here. Okay, so this is basically the updating strategy for the federated learning, federated training. Right? So we can see that for the server, right, it will perform the weighted averaging of the node core feature structure encoders by following the standard federated averaging method. Right? So here we can see that each coefficient for the aggregation is determined by the local node size. And also that for the structural proxy vectors, right? So here that we propose to assign high weights for the majority classes when we do the aggregation, because we consider that for these majority nodes, they have a more important role in the aggregation. Okay, so here that the alpha JK is a ratio of the neighbor nodes from the JS class in the client K. Okay, so here are some experiments. Right, so basically we choose many different real-world graphs, right, from different areas, right. So then we can basically make use of the community detection method, trying to split the graph into different clients, right. So we have some backbone models for the graph-based machine learning models, like the GCN, SGC, and GraphSage. So here are different baseline models we want to compare with. Okay, so this is experimental results. So we can see that, generally speaking, that our method, we call it a feather spray. Actually, it gets much better performance than many existing baseline methods. And if we look at this row, minority, basically we only focus on the minority nodes, right? So we can see that for the minority nodes, the classification performance improvement for our method actually is quite significant, right? So, so this also implies that basically by using some structural proxy vectors, basically it can mitigate the adverse information for the minority nodes. Okay. And here are some additional experiments. So here that we further validate the effectiveness of the structural proxy vectors, right? So we investigated the performance of our proposed method when the structural proxy vectors are removed. So more specifically that we set this structural proxy vectors to be 0, right, during the training. So we can see that without the structural proxy vectors, so the feature structure encoder generates a soft target only based on the node features, right? So in this case, that the soft labels may not be quite reliable. So they cannot provide some useful guidelines for the local training for the GM model, right? So this can also be observed from the results in the table. Basically, when we specify S as 0, so we can see a significant performance degradation. Okay. So as a summary, that for this talk, basically that the goal for this talk is that we're trying to study the federated learning in weak supervision situations, right? So because it's quite common in many real-world systems, especially the cyber-physical systems. Okay, so we actually discussed two different kinds of situations. So the first situation is that for some classes we have limited training data, right? And the second situation is that for the graph data, right? So basically, for the nodes from the minority classes, basically that we typically cannot get good performance for these nodes, right? So basically, that we propose two methods. Right, so the first method is kind of the decoupled meta-learning framework. Right? Basically, we have a server model, so that will be shared. And we also have a client model that basically will be used to learn some client-specific meta-knowledge. Right? We also propose some specific strategies to update the server model and the client model. right? So for the second piece of work, so the basic idea is that we're trying to learn some structured proxy vectors, but we hope that these structured proxy vectors can provide some useful high-level abstractions of the label information, right? So this kind of the structured proxy vectors can help mitigate the adverse information for the minority nodes. Okay, so yeah, that's all for my today's talk. And I will stop here and take any questions from the audience. Thank you.